For our introduction to limits, we spent a lot of time looking at graphs and using those to interpret the limit. We all know that graphs can be difficult to generate by hand, and they can also be difficult to ensure that they are accurate. So we need a more mathematical way to evaluate limits. Below is a list of properties that we can use with limits. For example, if we're trying to determine the limit of some constant, notice the x value doesn't affect it, so the limit is just the constant itself. Likewise, if we're trying to find the limit of x, as it approaches a, it's always going to be a. And then you can see here that we can add or subtract limits, we can multiply limits, we can divide limits, and then you'll see here we can multiply by a constant and bring that out. We can move the limit inside a square root, and if it's a polynomial, we can simply evaluate that polynomial. You don't need to memorize all of these particular properties, but you do need to be able to apply them. So let's look at an example here. For example, here we're taking the limit of 10 as x approaches 4. Well, x has no bearing on this, it's simply a constant, so the limit is going to be 10. And this relates to property number 1, the limit of a constant. Here, this second one, we're evaluating a polynomial and we want the limit of that. So we're simply going to plug in the value of x. In this case, we'll plug in 3 and we get 3 squared plus 5 times 3 plus 7, leaving us with 9, plus 15 plus 7 gives us a value of 31. And this we can reference as property 9 if you're looking at that. Here we can see that there's a square root and also a quotient involved, but also polynomials. We can bring the limit inside the radical as referenced in property 8. Then we can also split that limit to the limits of the quotients by using property 6. And then we can finally simply evaluate the two limits. Again, we're looking as x approaches 2. So we end up with 2 minus 3 over 2 plus 6. So we end up with negative 1 over 8, but we still have that square root. And I'm sorry, it's actually, let's go cube root here. That's what I meant to have there. And so we end up with negative 1/2 for our final value there. And again, make sure you make that a cubed root. Remember, we already discussed the idea that if an expression ends up as what we call an indeterminate, so something like 0 over 0, then we can factor out and remove that discontinuity. Well, let's review that again here. Notice if I'm looking at x squared minus 9 divided by x minus 3, if I want to know the limit of f of x as x approaches 3. Notice if I plug in 3 to the top, I get 0 and 3 to the bottom, which is an indeterminate form. But I can then factor the top into x minus 3 times x plus 3 all over x minus 3. The x minus 3's cancel, and now I can plug in the value for x since I'm dealing with a polynomial, and I get a value of 6. You'll see this is called a removable discontinuity because it simply creates a hole in the graph as shown here. Let's look at another example of this where we want to find the limit as x approaches 1. Again, if I plug in 1 to the top and 1 to the bottom, I do get 0 over 0. So if I factor, I can factor this using the difference of cubes. So I have x minus 1, x squared plus 2x plus 1 all over x minus 1. Again, those are going to cancel out, and then I'm dealing with a polynomial, which leaves me with x squared, which is 1, and I'm sorry, this should actually just be x because the formula is ax, which is just 1x. So I end up with 1 squared plus 1, which gives me 3 for the limit. But let's consider something like this. What if there's no way to factor out that discontinuity? Well, then we have to reach a different type of limit, and we have to have a different way to approach it. Because notice here, if I plug in 5, I'm going to get 1 over 0. Well, this is going to lead us to what we can call an infinite limit. Notice if I look at both the right and the left-hand limit, if I look at as I approach 5 from the left, notice down on the bottom, I'm going to have 1 over some negative number, which is going to lead me to negative infinity. And then if I approach 5 from the right, I'm going to have 1 over some positive number. And thus we see that the limit does not exist, and the equation or the graph is going to be unbounded in the negative direction from the left and unbounded in the positive direction from the right. So what about piecewise functions? Again, here we have something like f of x equals 2x for x less than 3 and x plus 3 for x greater than 3. If we want to find the limit from both as x approaches 3, then we have to consider both the left-hand limit and we have to consider the right-hand limit. Notice in both cases, here we are just dealing with the polynomial 2x, and here we're dealing with the polynomial x plus 3. When I plug in 3 here, based on those properties, I get 6. When I plug in 3 here as well, I get 6. And since the right-hand limit equals the left-hand limit, it is indeed 6. Let's consider now what happens when we look at, instead of x approaching a number, what about when x is approaching infinity or negative infinity, particularly for rational functions. In this case, remember, a rational function is simply a polynomial on top and the polynomial on the bottom. So let's consider this function. I've graphed it here, and as you can see, as x approaches infinity, it appears that this graph is leveling out. And likewise, as x approaches negative infinity, it also appears that it's leveling out. But how do we know what value it reaches? Well, we're going to look at that more algebraically here in just a minute, but let's consider another example. Here, I've graphed the same thing. As x approaches positive infinity, it appears to approach the x-axis. As x approaches negative infinity, it also appears to approach the x-axis. So it appears to be approaching a value of 0 for the limit. And last but not least, here if I look as x approaches negative infinity, this graph appears to be moving towards negative infinity as well. Well, there are 3 rules that we can apply for rational functions. Please note they have to be rational functions as x goes to infinity, or we can apply the same rules to negative infinity. Basically, you just have to look at the degree of the polynomials. If the degree of the polynomials are equal for the top and the bottom, then all you care about are the leading coefficients, and that's the limit it will reach. If the bottom degree, and so I have listed it here as bottom and top, if the bottom degree is bigger than the top degree, then the bottom plays a bigger role, and so eventually the limit will reach 0. And in contrast, if the top is bigger than the bottom, then the top equation is going to play a bigger role and it's going to approach infinity. So let's go back and look at these 3 functions that we just looked at graphically. Notice here the degree of the top is 1, the degree of the bottom is 1. So according to our rules there, the limit is going to be the ratio of the leading coefficients. And as you can see here, that is indeed where our function is approaching. And this is what's called a horizontal asymptote. And a horizontal line, we're going to have y equal to 3/2. In this case, notice the top is 1, which is less than the bottom degree, which is 3. That means that this bottom function plays a bigger role. So in that case, that means that we're dividing by a much bigger number. So eventually this is going to approach 0, as indicated here. And finally, if the top degree is bigger than the bottom, then it's going to approach, in this case, because we're going to negative infinity, a negative number of negative infinity.